Welcome everyone to this explainer. I'm absolutely thrilled to have you here today because we're going to dive into this crazy, hidden, silent chemical warfare that's literally destroying our built environment from the inside out. We walk past it every day, right? We live inside it, we drive over it, but most of us have zero clue about the microscopic battles happening right beneath the surface of the concrete all around us. So today, we're decoding the whole shebang, the science of concrete spalling, structural decay, and the advanced engineering required to stop it in its tracks. Let's kick things off with a quick game of Spot the Risk. So, imagine you're walking under a concrete balcony, or maybe you're looking up at a highway overpass, and you spot this small, kind of innocent-looking brown or orange stain right on the surface. Now, as someone who knows a thing or two about infrastructure, I want you to ask yourself, is this just a paint issue? Like, did someone just spill their coffee? Or are we looking at the very first warning sign of severe structural decay? Well, if you guessed structural decay, you hit the nail on the head. You are entirely correct. That little stain, it's basically the tip of the iceberg. What you're actually looking at is a symptom of a slow-motion, macroscopic structural explosion that's happening from the inside out. That brown streak is literally ferrous oxide, rust, just bleeding out through microcracks in the concrete. It means the steel reinforcement, the stuff that gives the concrete its essential tensile strength, is actively corroding and losing its load-bearing capacity. No way around it. Okay, let's dive into Section 1, the microscopic battle. To really grasp why this massive structural failure happens, we've got to zoom in. We're transitioning from that visible damage we see on the surface to the microscopic chemical war raging inside the concrete slab. It all starts with the chemistry of the cement itself. Under normal, healthy conditions, the water inside the pores of Portland cement concrete is highly alkaline. We're talking about a pH level hovering right around 12.5 to 13.5. This alkaline environment is absolutely fantastic for steel rebar because it forms this passive gamma ferric oxide layer right on the steel surface. Think of it as this invisible rust-proof shield. But then, carbonatation happens. Atmospheric carbon dioxide penetrates the concrete, reacts with the calcium hydroxide, and forms calcium carbonate. This steadily drops the internal pH. And once that pH falls below 9.5, poof, the steel's armor is entirely stripped away. And this brilliantly illustrates what's going on. Think of that high pH alkalinity as a protective passivation bubble wrapped tightly around the steel rebar. As long as that bubble is intact, your steel is safe. But carbon dioxide acts like this slow-moving needle, while chlorides, like the stuff from coastal sea spray or de-icing salts on the roads, act like aggressive darts. Once they penetrate deep enough to reach the steel, bam, that passivation bubble is violently popped. The steel is now totally exposed to moisture and oxygen. So let's walk through the mechanical before and after life cycle of this destruction because it's pretty wild. First, passivity is lost. Second, the unprotected steel oxidizes and turns to rust. Third, and this is the absolute critical mechanical failure here, that rust expands to occupy 6 to 10 times the volume of the original steel. Let that sink in. Fourth, this massive expansion generates internal radial pressure that quickly exceeds 5 megapascals. That's roughly 725 psi, a crushing amount of internal force that just completely overwhelms the concrete's natural tensile strength. And finally, step 5, the concrete literally pops. It just fractures and blows apart. This right here is what we call spalling.
All right, moving on to Section 2, honeycombs and cover failures.
Now that we've got the chemistry down, let's take a trip to the construction site and see how this builds into an even bigger problem. Basically, human error during the pouring process dramatically accelerates this chemical decay. The main culprits? Honeycombs. Those ugly, hollow spaces and cavities left inside the concrete mass when the mortar just completely fails to fill the spaces between the coarse aggregate. The causes are pretty clear. Poor workability of the mix is a major one. Then there's improper compaction. Like if you over-vibrate, the mix segregates. Actually, on the flip side, if you under-vibrate, you leave air pockets. Other causes include rebar congestion, where the aggregate just can't squeeze through, leaky formwork that lets all your binding grout escape, and of course, poor aggregate grading. So the crucial point here is simple, but honestly devastating. It doesn't matter if an engineer specified 3 inches of concrete cover over the steel. It just doesn't. Because if that cover is full of honeycombed voids, it's completely useless. Those hollow spaces act as like superhighways for oxygen, moisture, carbon dioxide, and chlorides to bypass the dense concrete cover entirely and drive straight into the heart of your reinforcement. Basically, your protection has failed before the building is even finished. This brings us to a massively important practical site demonstration. Now, on the left side of our comparison, we have proper engineered plastic mesh spacers. They clip on nice and securely and have a large base to protect the damp-proof membrane underneath. But on the right, yeah, this is a dangerous, all too common site practice. Lifting the steel with a random brick or pulling it up with a hook during the pour. A brick is highly porous, right? It traps moisture right up against the steel and creates structural voids. Guys, lifting steel with a brick is exactly how spalling is born. It is a guaranteed future failure for sure. Next up, Section 3, Concrete Exposure and Protection. So, how do professionals actually calculate defenses against this stuff? Well, they rely on specific exposure classes, like the ACI 318 code, to determine exactly how much defense a slab needs based on its environment, and the data clearly distinguishes between interior and exterior requirements. For a mild, dry interior, you might just get away with 20 millimeters of cover, but step outside into moderate rain, you need 35 to 40 millimeters. Move to a severe coastal or high moisture area, and you're looking at 50 millimeters minimum. And remember, context is everything. In regions like Pakistan, for example, you've got high humidity paired with extreme seasonal temperature shifts, which rapidly accelerates the expansion and contraction cycles of the concrete. This makes sticking strictly to these proper cover minimums absolutely critical, way more so than in mild or arid climates. But what happens when an older structure is already compromised? Well, engineers don't just guess. They use rigorous diagnostic protocols. They use cover meter surveys to map out the exact steel depth. They use half-cell potential mapping to find hidden electrochemical corrosion activity before any physical cracking even appears on the surface. They drill dust samples for chloride ion analysis to check for pitting corrosion, and they do pull-off testing to make sure the remaining concrete is actually strong enough to hold a repair. Now, when it's time to actually fix the spalling, we have to prep the site properly. Professionals strictly follow what's called the square-cut rule. You don't just slap a patch over the rust. No way. You mechanically break out the contaminated concrete, and you absolutely must avoid feather edging, which just leads to the patch flaking right off. Crucially, you have to break out at least 20 millimeters of concrete behind the reinforcement bars. Why? So the new repair mortar can flow all the way around the steel, completely encapsulating and protecting it.
Which leads us to our final section, Section 4, Advanced Structural Remediation.
Now, what's really interesting about this slide is how we resurrect a slab that has already lost a massive amount of its flexural and structural capacity due to corroded rebar. The contrast between the past and the future of structural strengthening is just staggering. Traditionally, if a slab lost its strength, we'd bolt these heavy, thick steel plates to the underside. But those plates are heavy, they're super hard to install overhead, and honestly worse, they are susceptible to the exact same corrosion that ruined the rebar in the first place. Today, though, it's a real game changer. We use CFRP, carbon fiber reinforced polymer systems like TIFO. CFRP has a massive strength-to-weight ratio. It's chemically inert, meaning it will literally never rust, and it's only 2 to 5 millimeters thick, meaning you don't lose overhead clearance in places like basement parking garages.
But, fixing the structural strength isn't enough if you don't stop the underlying chemistry. If you just patch a hole in a chloride-contaminated slab, the difference in electrical potential between your brand new patch and the old, salty concrete around it actually accelerates corrosion in the adjacent area. We call this the incipient anode effect or the halo effect. To prevent this, engineers deploy an advanced toolkit, zinc-rich epoxy primers, and sacrificial galvanic anodes that generate a small current to protect the steel. Then we finish the whole thing off with anti-carbonation breathable coatings and silane-based water repellents to lock moisture out for good.
Which leaves us with this final, provocative thought. Next time you walk through your city or park your car in a concrete garage, I want you to look closely. Are those recent patch jobs really fixing the problem? Or are the buildings in your city hiding the incipient anode effect right now, just silently waiting for the next spall to blow? Thank you so much for joining me on this explainer. Keep your eyes open, stay curious, and I'll catch you in the next one.